Good morning. My name's Hannah Ditto, and I'm an electrical engineer, and I'm joined by my colleagues Daryl Grunvelt and Kyle Connell, who are also electrical engineers, and we are Team Acumentrics Volta. Our project is automated variable load testing of high voltage DC output boards. Like the other group mentioned, Acumentrics is a company located in Walpole, Massachusetts. It was established in 1994. They focus on U.S.-made power electronics. Specifically, we are working with the RUPS, or Rugged Uninterruptible Power Supply. This board is made up of approximately over 20 circuit boards, and we're working with the DC to DC output board and the charger board. The picture on the left shows the current test station at Acumentrics testing facility. The way that they are currently testing their boards, they use a selection of them attached to a heat sink. And the board there is the charger board, which is one of the ones that we're working with. Our project will save Acumentrics a lot of time and money because you'll be able to test each board individually and prevent failures. Currently, the manufacturer will send it to Acumentrics, and about 1 in 4 boards are damaged. Our anticipated best outcome is to create a functional prototype that performs an automated load test. We collect values and compare it against the specifications of the boards, and then have a visual indication to the user through LabVIEW if the board is passing or failing, if there's some connections that are wrong, things like that, and then also log data. The way that the DC board currently works is it takes a 200-volt DC input. The enabled signals are 15 volts and 3.3, and then it outputs 28 volts. The 28, this is a specific picture of the DC board. Again, the input, the enabled signals, and the output. The 28-volt output is the military standard voltage. The charger board works very similarly, taking the 200 volts in, that has the enable signals of 3.3 and 2.9 volts, and then outputs the same 28 voltage. The function of the charger board, it charges the battery so that if the input is cut, then the battery will kick in and then still supply that 28 volts.
So we've been able to accomplish some key important tasks for the benefit of our project, and that includes creating a high voltage safety test environment as well as documented safety information, determining the most beneficial equipment for our project in order to get the job done, as well as maintain that safe environment, determining the testing process so it can be followed from start to finish, as well as automation of that testing process so that there's very little input required from the test operator, and a pass or fail system that is indicated to the user upon the completion of the test. So here we have a picture of our current testing setup. On the left we have our DUT enclosure, which is responsible for housing the board as well as the connections. On the right we have our programmable DC load, which serves the purpose of mimicking whatever object is requesting power from the board or system. Currently, for our high voltage power source, we're using Acumentrics UPS. Then we have our low voltage power source, which is responsible for supplying the enable signals to our boards. And these signals first run through our data acquisition unit, which we've determined the Keysight DAC 970A to be the most beneficial for its use with 2 particular modules. And that consists of a multiplexer and a switch actuator. And the purpose of the multiplexer is for reading the input and output voltages from our system. And here we can see we have those signals running into that board. And the switch actuator serves the purpose of being able to switch on and off our enable signals during the testing process for the purposes of automation. So with that equipment, we then had to design wires and connectors in order to be able to switch the boards in and out easily for testing purposes, as well as get everything communicating properly. And the key aspect of this project was to create an automated testing process for these boards. And in order to do that, we first had to understand and define the manual testing process. So we did that by recording data and working with the specified operating parameters of each board to then, in turn, transfer that information into LabVIEW, which is probably the most difficult part of the project, but LabVIEW is a visual programmer that allows the user to create virtual interfaces that they can interact with through the use of block diagrams, as well as being able to communicate to external devices. And here we have one VI that we created. So we went through that process to create VIs for each board as well as external device. And this particular VI is for interacting with our load. It's slightly intimidating, but that's why I'm here to explain it to you. At the top, we have our main flow of data, which is intended to communicate with the load itself. We then have values being read in orange, most importantly voltage, and that runs through a system of equations, which then goes through Boolean logic and returns a state to the front panel, which serves as LabVIEW's user interface, which we are currently designing to be as user-friendly as possible so that anybody can go through the testing process easily. And of course, another key aspect of this project was creating a visual pass or fail indication to the test operator, and we can see that in the blue, green, and red LEDs in bold fashion. And with that, we'll talk about our future plans.
So my name's Kyle, and I'll be talking to you about our remaining technical challenges along with our extended best outcome and our team's acknowledgments. For our remaining technical challenges, we'll be integrating an AC and DC power supply into our pre-existing LabVIEW codes. This will automate the voltage completely coming into the boards, and it will allow AC as an input for the boards that need it for our extended best outcome. We'll be introducing a data log function, which will produce a spreadsheet of the parameters of the boards from start to finish of testing. This will help if there's a failure in the board. The user will know exactly what the parameters of the board were when it failed, and will help manufacturing discover the problem for fixing the problem. And over winter break, we'll be integrating our LabVIEW codes into the company. They will be putting it into the manufacturing line where they'll be testing the boards there. And from there, we'll be receiving feedback of the front panel and the message prompts, seeing how the user interacts with the code. And we will update them accordingly and see how the user deals with it. And this brings us to our extended best outcome. This is what the 1U blade looks like fully assembled. Our anticipated best outcome was to focus on 2 of these boards. Our extended best outcome is to create LabVIEW codes for the remaining 20 boards. From there, we will be learning the input and output functions of the remaining 20 boards, along with creating voltage reader VIs for the remaining 20 boards. After that, we'll be creating a master VI, which will call all the single individual voltage reader VIs into one single file. From there, the user will run the code, and it will cycle through all the individual voltage reader VIs, and all the user will have to do is cycle out the boards, and the message prompts will display the next step for each board. And this helps Acumentrics because, like Hannah said, 1 in 4 boards that come to the building are a failure. Having this at the manufacturing company will allow all the boards going into Acumentrics being a working board, which will increase production, and it will make, yes. And these are our acknowledgments.